In this video, we're going to focus on variable acceleration, which is converting between displacement, velocity, and acceleration. So there's a little trick I like to tell my students when converting between them. Honestly, just draw S, V, and A to represent displacement, velocity, and acceleration. Sometimes you might see displacement represented by a position vector, which is like a bold R or even an R with an underscore underneath it. But yes, just so you're aware. Whenever you go to the right, you want to differentiate. For example, if you want to get to velocity from displacement, you differentiate displacement to get to velocity. You differentiate velocity to get to acceleration. Whereas whenever you go to the left, you want to integrate. So for example, if you want to go from acceleration to velocity, you integrate it. And if you want to go from velocity to displacement, you integrate it. In this video, sorry for the handwriting by the way, in this video I'm going to go through both of those examples, and I'm going to make my pen a little bit thicker just so it's easier to see. Here it's giving you an equation for velocity. It's also told you after 5 seconds the displacement is 75 meters. I'll tell you why that's important. It tells you then to find the displacement from the velocity. So if you want to go from velocity to displacement, what do? You integrate velocity. So we say the displacement, S, is what you get when you integrate the velocity equation, which is 6t minus 2. Because everything's with respect to time here, we're going to integrate the variable t. Just a reminder of integration, you add 1 to the power and you divide by the new power. And you apply that same concept here. So it's like 2t to the power of 1 divided by that new power of 1. You also have to remember to include the plus c because there's no limits involved. Now 6 over 2 is just 3, so this becomes 3t squared. 2 over 1 is 2, so that becomes minus 2t. So we have the displacement is equal to this plus c. But we now have to find the value of plus c, and that's where this bit of information comes in useful. It tells you that when t is equal to 5, the displacement is actually equal to 75. We can put that into this expression and get that 75 is equal to, well, t squared is 5 squared. 5 squared times, is 25, times 3 is 75. Minus 2 times 5, which is minus 10, and then plus c, in which case c is just going to equal 10, because minus 10 plus 10 will get you 0, and then you get 75 equals 75. Now that we've got the value of c, we can input it here, and we get the final equation for displacement. That's as far as you need to go for this question. It then tells you in part B to find the displacement after 10 seconds. That's pretty easy, honestly. You just put t equals 10 into the displacement equation. You've done the hard part. In that case, s is equal to, I would show the working out, so 3 lots of 10 squared minus 2 lots of 10 plus 10. 10 squared is 100. 100 times 3 is 300. Minus 20 plus 10, and that's equal to 290 meters. That's everything for that part of the question. So that's where you've integrated to get to a variable. Let's now talk about differentiation to get to a variable. But before we do, I just want to mention something about the term instantaneously at rest. If you imagine a ball bouncing off of a wall, let's say its speed before bouncing on the wall is 6 meters per second, but after it bounces on the wall, the speed becomes 2 meters per second. Are those the individual velocities? They're actually not, because velocity is dependent on direction. So in one direction, if you take it as positive velocity, the opposite direction has to have a negative velocity, for example, minus 2 meters per second. That's very important because if you go from a positive to negative velocity, at some point, while the ball's bouncing on the wall, its velocity has to be 0. Otherwise, you can't go from a positive to a negative number. That position where the velocity is 0 is where we say the particle is instantaneously at rest. So whenever you see the phrase instantaneously at rest, you want to think to yourself, okay, I'm going to find the velocity equation and make it equal to 0. And that's exactly what we do here. How do we get to velocity from the displacement? Well, let's see. You differentiate displacement to get to velocity. So we say velocity is a differential of all of these variables. Now 2t cubed differentiates to 6t squared, minus 18t squared differentiates to minus 36t, and 48t just differentiates to 48. And like I mentioned before, we're going to make the velocity equation equal 0 now. Now, when solving quadratics, if you're able to, I would recommend dividing by a constant to make it easier to solve. For example, here, all of these 3 terms are factors of 6, multiples of 6. So you can divide each individual term by 6. That then becomes t squared minus 6t plus 8, all equals 0. From there, it's pretty simple factorizing, which I'm sure you guys know how to do. And you get 2 solutions of t, either t equals 2 or t equals 4. That tells you that the particle changes direction when t is equal to 2 and t is equal to 4. That's very important for the next part of the question, which we're now going to have a look at. What most students do for this question is they put t equals 0 into it, the displacement equation, and then t equals 5 into it and find the difference between them. But what we've established is that it changes direction when t is 2 and when t is 4. So what we have to do is draw a displacement time graph. So bear with me if you're struggling to understand this a little bit. Between t equals 0 and t equals 5, we know that when t is equal to 2 and t is equal to 4, it changes direction. When you put t equals 2 into the whole displacement equation, you get 40 meters. I've done it before, which is why I know this. I'm not just kind of genius. When you put t equals 4 into this displacement equation, you get x is equal to 32. X, by the way, is just displacement in meters and time in seconds. And then when you put t equals 5 into it, you get 40 meters again. So the displacement time graph looks something like this. In that case, is the distance traveled just from 0 to 40? No, actually, it's not. It's this distance that it travels initially, 40 meters, but then it travels another 8 meters while it changes direction, and then it changes direction again where it travels another 8 meters. So the total distance traveled is 40 plus 8 plus 8, which is 56 meters. And that's your answer to this question. Hopefully that all made sense, and that's the main type of question that does come up. Of course, there are some irregular, more difficult questions, but yeah, I thought I'd make a quick video going through this. Thanks for watching. I hope this video helped. If you have any tutoring inquiries, be sure to visit my website www.excellineducation.co.uk. It's on the first link in the description too.